I would like to welcome to the floor our next speaker, Fédor Galkin, Director of Scientific Business Development for Deep Longevity, to share his insights on finding the path to personal longevity with AI systems. Fédor, it's great to have you back with us. The floor is yours.
Thank you for the introduction, Franco. And yes, today I would like to give more of a slightly more technical talk than I usually do. Because I will be talking about how in deep longevity we look for the ways to improve a human lifespan, right? And the very core of this approach is how we generate recommendations. So my name is Fédor Galkin. I'm the Director of Scientific Business Development in Deep Longevity. Just a quick disclaimer before I proceed is that Deep Longevity is part of a publicly traded company called 𝐁𝐢𝐨𝐦𝐚𝐫𝐤𝐞𝐫𝐬. And initially we were incubated in Silicon Medicine, but now we are our own startup company under the wing of 𝐁𝐢𝐴𝐦𝐚𝐫𝐤𝐞𝐫𝐬, doing biomarker research, producing aging clocks, and finding the applications for this technology for clinics, for insurance companies, pharmaceutical companies, and other sectors. So the very idea of measuring age and the processes of aging is somewhat tough and hard because, first of all, there is no general consensus on what exactly constitutes aging. For example, we can ask the question of when does aging start? Right, there are several answers to this question. We can consider it from the mortality curve, that perhaps it is at 30 years when the mortality curve goes exponential finally, right? It has somewhat of a flat line in the 20s. Or we can say that, this curve is dropping until early teens, but then it starts rising. So perhaps people start aging when they are when they are still children. But we can provide even more points of view. So we can say that as soon as you are born, because some mechanistic theories of aging say that, well, mitochondria and reactive oxygen species, they are the root cause of all aging processes, well, most of them. So, and as soon as people start breathing, they start generating these reactive oxygen species, and the mitochondria start, well, slowly killing us. So there is this point of view. And yet another is that, well, aging actually starts before inception because, for example, the rate of mutations that are introduced into your genome, it greatly depends on the age of your father. And also, if I have already told about mitochondria, so we get all our mitochondria from our mothers. So the mutations that our mothers acquire throughout the years, they might actually also go into the following generation. So we can argue that aging starts even before inception. Yeah. So with all these slightly confusing plethora of ideas of what aging is, it's really hard to navigate all this space, especially if you're a consumer and you have asked somebody just a simple question, well, hey, how do I live longer? What do I do? And you start unpacking what aging is, etc., etc. It's very confusing for a consumer. And the people just, I think, want to know how to live longer, healthier, and happier lives. So, oh yes, another way of showing what that aging is totally different depending on the point of view. This is a work by Vadim Gladyshev, and what he actually did, he tested in mice different anti-aging geroprotective therapies and found out that all of them, well, here are the columns, and each column is a geroprotective intervention, treatment, or a genetic line of mice that are supposed to live longer than normal mice. So what he found that the gene expression in all these different mice who are supposed to live longer than usual mice, they are totally different. So these genetic signatures of aging they depend on the model you are using at the moment for your experiments. So even if we read in the articles that, well, this new silver bullet pill, it treats aging, well, it might be true for example, these cluster of aging processes, but these who are totally different by gene expression, these magic bullets pill will not work, right? So aging remains somewhat undefined in the field. And we decided that, well, since there are so many opinions on what aging is, why don't we try to combine them into, well, you know, this kind of arsenal of different approaches to studying aging, and build a small treasure chest where we keep all the different theories of what actually is aging, and each theory gives us answers on how to treat aging and how to fight it, how to slow it down. We have built a number of aging clocks to tell how fast people are aging, and each one of them can tell us very important tips about this particular person, right? We have a psychological aging clock. We can extract tips on how people should think to stop their aging, right? We have ECG aging clock. So this project can tell us more about what people who are mostly concerned about the aging of their heart system, of their cardiovascular system, what they should do, and all these other different types of aging clocks to fit every possible answer to what aging is, when it starts, and what actually you want to achieve when you say, I want to stop aging. All our aging clocks are realized as deep models. Well, in the context of other, well, they're called here shallow models, but I guess the proper term is linear models. All our aging clocks, they use lots of data obtained from public and not so public sources. Sources of when we partner with somebody, and we might get some rare data set in collaboration with somebody. And we use these data to estimate someone's biological age, which represents the intensity of the aging processes they're going through, not just a simple number in your birth certificate that says, well, you are 60 years old, but you might be actually doing really well, aging very, very slowly, and your biological age might be 40 years, right? In this case, we say your aging rate is decelerated, so you are doing good. And conversely, if somebody is 20 years old, but their biological age is 40, well, they definitely could could use some help from us, from our aging clocks and our recommendation systems. So I have already introduced the concept of multifaceted aging, and that we have an aging clock for every facet of aging. And I like to imagine it as some kind of a pyramid, and it is much easier to affect the higher levels of this structure, much more difficult to achieve something at the bottom. And but at the same time, the features that are on the top, like psychological age, how your habits, how you produce your habits, whether you're a physically active person, well, you can probably easily imagine how to change that. You can tell a person that, well, you should stop drinking so much alcohol, or you should drink more green tea, and this will help you immensely. So this is something that people can easily do, but at the same time, the variability of aging rate we can detect using these two layers is so high that we need to observe a person for a long time before we can we can be sure that their aging rate is accurately measured, and that our recommendations are helping them So you need to have a long-term observation of a person to see that your recommendations are helping them, and that they are actually on the right path to longevity. The bottom two layers are blood age, so that is blood biochemistry, complete blood count, and metabolic profile of your blood. If this aging clock, our blood age clock, it produces much more accurate estimations, and they are much more medically, clinically relevant than, for example, psychological aging estimations. And if, but at the same time, it's hard to influence this. You need to probably use some medications, see a doctor, see a physician, and ask for their advice, and follow, for example, a regimen of supplementaries, vitamins, etc., etc. And eventually, you will change the aging pace associated with your blood system. And well, we know that blood permeates all organs, and that is why it is so useful as a source of biomarkers of anything. Yes, you have bad liver, you can see it in blood. You have bad heart, you can see it in blood as well. So aging, if you have fast aging, you can see it in blood as well. That is what we do. And the very bottom is this category of molecular aging clocks, right? We have here transcriptome, microbiome, epigenetic clock. So these aging clocks, they might be very hard to shift backward. You need to keep your new lifestyle, your new pro-longevity lifestyle for months before these changes, they trickle down through all these levels and settle down in your epigenome, right? So, but once they are there, it's the good point. It will be really hard to get them out. Yes, to lose these milestones of slow aging. So I will start unpacking these rather quickly. So the first thing is that psychological aging, what we do is currently we are researching the theme of when a person can be said that he is maturing or is he aging. For example, in our study from last year about psychological aging, we see that, for example, openness and extroversion, lots of really good stuff are associated with higher psychological age. So people who are psychologically older, they display, well, for example, higher conscientiousness, and conscientiousness is good. So no arguing here. And at the same time, people who display low psychological age, they're high in neuroticism. So is this aging or is this maturity? This is actually some kind of an open topic. And right now, if you look at, if you type in Google, is happiness U-shaped, and the U-shape of well-being, you will see lots of articles dedicated to this topic, whether people are generally declining in their well-being and happiness, and whether everybody wants to always be younger, or there is this kind of U-shape. And what we believe that in many cases, people do not want to be unconditionally younger. There is some kind of desired age that they should move forward to. And we are currently developing this idea, and hopefully in the following months, this will be released in publications, in applications of iPhone and other services that will help people to reach their desired age. Blood aging, I have quickly, briefly mentioned it, that we get 2 blood panels. You can estimate age really accurately. Right here is actual age and the predicted age on the y-axis. The best, well, I say that they are perfect fit for clinical trials. Why is that? Because in many clinical trials, you get information about how different compounds affect your blood levels. And in some cases, well, you can take information collected across different clinical trials, And this is something that we did in-house and tested, for example, how niacin, how it affects aging, right? So you can measure your your subjects in a clinical trial before and after they were subjected to a novel treatment or a hypothetical geroprotective intervention, and see how their blood levels change in the context of aging. And why it is perfect for clinical trials, because in most clinical trials, all these blood biomarkers, they are just part of a standard package. You usually take these blood biomarkers from people, measure them. So testing whether some kind of intervention increases or slows down the pace of aging is no big deal. And finally, we're at the very bottom of our pyramid, is as represented by epigenetic aging. We have a model called 𝐁𝐢𝐨𝐬𝐚𝐫𝐤𝐞𝐫𝐬, and what we can do with it is we can estimate which genes are for example, too methylated, and if they were slightly lower methylated, right, they had a lower concentration of methyl residues on their promoters. Each one of them, well, on average, that would decrease your biological age by 1 year. Yes, and you take 1, 2, 3, 4, 5 genes, you reduce their methylation level, and a person might get younger by 5 years. That is something that we are actually also developing. I might actually briefly say how we achieve that. Well, first of all, we have annotated all the genes used by our aging clock, and we have also collected lots of literature references, how to see how the things from, I don't know, from your dietary habits to the levels of stress you experience on your work, how they affect your methylation levels. And through these interventions, we can estimate how people will get younger or older. And just a brief technical remark is that to do that, I think we solved a rather hard technical issue with feature importance, right? So the very foundation of any, I think, recommendation system that we use in with our deep aging clocks is feature importance analysis. So we need to find which features increase your age in a specific person. And to do that, well, one way is to use LIME. It is a rather popular method in the deep learning community. So what LIME is basically doing is it is sampling many pseudo samples around the original sample, and you predict the age for all these people. For example, in this case, we did 2 runs of LIME on the same sample, 5,000 pseudo samples, yes, mock epigenetic profiles for for one person. And we can see that in most cases, the effect that these 2 feature importance analysis runs produce, they correlate really well. So if in one iteration we see that a methylation level increases your pace of aging, that in the second run we will see the same. Yeah, so the randomization does not really affect the stability of this method too much. Same goes here, and very few outliers, right? So for example, here run 1, the first run said that these DNA methylation mark, it actually makes a person look older, but the second run said that this mark makes a person look younger. So among the 5,000 samples, it is really 10,000 in total, right? It is a really rare occasion. So yes, I think I'm done with my presentation. I hope I'm not too I'm not too out of schedule. So if you would like to, yeah, oh, thank you. Great. So I will have some time for the finishing word, right? So yes, if you have any questions and you would like to discuss academic collaboration or commercial collaboration, or just to talk about the technical implementations, I'm always open for dialogue or a video conference call. You can directly send me an email, Fédor@deeplongevity.com. You can scan my WeChat. I'm always on WeChat. It's the app I use the most. And if you are interested in how aging clocks could help you in your clinic, in your company, scan this code and it will redirect you to a Google form that will help us learn more about each other. All right, thank you.
Well, thank you so much for that, Fédor. And any interested viewers who do have specific questions for him, feel free to pop those into the Q&A box below. Yes, thank you. Thank you, Fédor. Insightful as always. And I personally very much liked the technical nature of your talk today. So thank you.